I really want to thank you for that very generous introduction, and to also thank the Weaver family. It's a real honor to give this lecture this year, so thank you very much. And thanks to all of you for being here. I thought it would be important if I first set a context of when my research went left field and started to focus on science that was relevant to young people who come into the context of our legal system. And this was a period in time, even before Roper, the Supreme Court decision to abolish the death penalty for juveniles under 18. And the reason that this time had such an impact on my research is that I was hearing my very valued colleagues, journalists and policymakers, comparing adolescence and the adolescent brain to a defective car, as if there were no steering wheel, no brakes, just an accelerator. And in part, these descriptions were used because evidence was being presented to try to show diminished responsibility of young people for their crimes, and thus these statements would impact less harsher sentencing for these individuals. The problem is some of the statements that were made about the adolescent brain included they have no prefrontal cortex, a region involved in decision making, and also, in self-regulation, along with other regions of the brain. And adolescents have a prefrontal cortex, in case you didn't know. We have all our brain parts when we're born. The only thing that changes with age and experience are the way those brain regions communicate with one another. And so I'll give you some evidence of that today. And also, it's the case, for many of you, you weren't adolescents that long ago. For me, it was more years, but I still interact with adolescents. And I know they are better than me and faster than me in making decisions when they have the information and they're given time to accumulate evidence to base those decisions upon. So a big question in my research has been really to try to understand the circumstances in which adolescents appear in their cognitive abilities like adults and situations in which they don't. And lawmakers really do not like for you to have a gray zone in terms of when we have full brain maturity and cognitive maturity. They want an age demarcation, but that's not the way we develop abilities, and it's not the way the brain develops. And I should just note that the reason why I'm underscoring that adolescents can be just as effective as we are in making decisions in certain situations is if we use this overgeneralization about the science to try to protect them from harsh sentencing, we can also end up taking away their rights, suggesting they can't make their own decisions. They can't make informed personal decisions about their medical care. And it could also lead to us taking away even more rights from them. So the main questions today that I want to touch on briefly, in what context does self-control or these cognitive abilities appear adult-like? In what situations are they diminished? How might learning about the brain help us understand these changes in behavior? And then this question that I get from judges and policymakers all the time: when does the brain and the capacity for self-control mature? Which, as a neuroscientist, I have a visceral response because we are all a work in progress. Our brain is continuing to change every day, even for me and several others in the audience. And then I want to end on how understanding brain and behavior has already informed the treatment of youthful offenders and how it may continue to inform our treatment of them in the justice system going forward. And most of the research that I'll talk about today uses the technology of magnetic resonance imaging, or MRI. With this tool, as adults, we can almost voyeuristically look into the brain of adolescents, and we can look at changes in structure and function and connections, those connections where communication across different brain regions is actually changing with age and experience. So First, just want to underscore again, the brain has the potential for change throughout the life course. We refer to that often as plasticity. But there is especially potential for change early in development, in these first few decades of life. And so what I've plotted for you here is really about those connections I was talking about, what's changing. And we see when we're born, we have more connections than we'll ever have as an adult. And with age and experience, we prune or eliminate irrelevant connections in the brain, shown in gray and illustrated in gray on the brain to your left. And those relevant connections are strengthened. And that's crudely measured by white matter volume, which you can see white matter tracks in this brain and here, and also the white tissue. So basically, these changes that are occurring with development makes the brain much more efficient and fast in the communication across many different brain regions. So across all the studies of the brain, I'd say hundreds of studies with thousands of participants, there's one region that we continue to see across a number of measures, whether it's connections, gray matter or white matter, that has a later development. And that's the area of the prefrontal cortex. This region, again, has been implicated in decision-making, future planning, impulse control, and regulation of ourself, particularly with regard with how it communicates with other brain regions. And I just want to illustrate in this movie, this is looking basically at gray matter, how that's changing in the cerebral cortex. And you're seeing those areas that are changing in blue sooner are the ones that are reaching adult levels of cortical thickness. And there's some areas that are taking longer. Let me use a static image to illustrate this. The bottom half of this image, we're seeing from roughly 5 to the early 20s. Those areas in blue here are areas in the motor cortex and in the visual cortex. It makes sense that systems that involve with us being able to see and to move would develop before the area of the prefrontal cortex, which uses that information to guide goal-oriented and socially appropriate behaviors. Now, I don't want to be a cerebral cortex chauvinist and just focus on it. Many people have, but when we think about adolescence, it's not necessarily about control or the functions of the cortex as much as it is about emotions. So it's the case that while we're seeing this development of the prefrontal cortex, functionally significant changes that extend into the 20s, we're also seeing peak changes in emotional systems of the brain, involved in gains versus losses, rewards, or threats. And we sort of simplified this in a description as an imbalance model, such that there's an imbalance between emotional circuitry in the brain and prefrontal circuits. And so in emotional settings, when making a decision, that earlier development or that peak changes that we're seeing in those emotional centers can potentially hijack our prefrontal cortex and related circuitry into making a more emotional decision as opposed to a rational one. And so I want to provide examples of tasks that we use in the lab to measure this. And one of the hallmarks of cognitive development is something we refer to as cognitive control, or our ability, I'll also refer to it throughout the talk as self-control. That's the ability to inhibit inappropriate thoughts, desires, and actions in favor of goal-oriented or socially appropriate ones. And there are a number of ways that we can measure this, but I'm going to use one, and I want it to be an anchor throughout the talks today because we're going to do subtle experimental manipulations so I can show how we can change an adolescent's ability to perform these tasks just by the context in which they're performed. So this is a go, no-go task. Majority of time, you are detecting a target, in this case, a mole. We've made this a fun task for children, adolescents, and quite frankly, I think adults enjoyed it the most. And then there's a rare no-go target, which is a vegetable. And I grew up a farm, so I know that eggplant don't emerge magically from the ground. But my RAs, they grew up in the city, do not. So anyway, for you to get a feel for the dynamics that are used in this task, I want you to play along with me. And I want you to say whack whenever you see the mole. And it's going to be kind of tricky, okay? All right, so get ready. I want you to go as fast as you can. Okay, you're going to have to be a little bit more enthusiastic and quick. I know, at the law school, you can be. All right, here we go. Did anybody? Okay. Wow. There's such control here. Or did I miss someone who said what? Okay, so let me just plot for you performance on this task from childhood to adulthood. And basically what you're seeing is that by the mid-teens, really you're almost as good, if not better, than some adults. And then for some of us who may perform this task, we may be way out here in our performance, and maybe in our age too. Okay, so this notion of us being able to have similar cognitive performance as adults has been shown in many studies. I'll just highlight another one that was funded by the MacArthur Foundation, a slightly different network than the one that Owen led. And that's looking at a number of basic cognitive abilities and across almost 1,000 young people, seeing how they perform. And again, you can see that the performance starts to plateau or reach asymptote by the mid-teen years. This development is different from something that we call, or Larry Steinberg has termed, psychosocial abilities. And that's when you have to make decisions or actions in emotional or social settings. And the development of those abilities are much later and tend to map on more in terms of the changes that we see in the prefrontal cortex and its connections with other brain regions. So it extends into the 20s. So let me just unpack what I mean by psychosocial abilities and two components of it. One is sensation seeking, so influence of peers, that sensitivity to rewards, and another is our ability to regulate ourselves when there are peers or when there's a possibility of a gain versus a loss. And you can see the developmental profile in these two aspects of psychosocial abilities is that sensation seeking peaks during adolescence, whereas self-regulation is still showing a steady increase that begins to asymptote by the mid-20s. And I just want to note that this pattern has been replicated around the world in different countries, showing a similar curve of sensation seeking peaking around adolescence and self-regulation continuing to show development. So now what I want to do is illustrate some experiments we've done in the lab to look at aspects of sensation seeking, and then on top of that, I'll add examples of regulation, self-regulation. And if we're sensitive to rewards, one reward that we're all fairly sensitive to in our society is money or monetary gain. So the question very early on, when we were hearing these descriptions of the adolescent brain there's no prefrontal cortex, so they can't make decisions. And we were like, the logic behind that doesn't flow because what adolescents do is very different from children. And children have an even less mature prefrontal cortex. So what else is going on in the brain that might drive their risk-like performance and behavior? And so we looked at the representation in response to rewards, building on elegant animal work that had already sort of mapped out this reward system and reactive part of their task. But instead of using juice as a reward in these abstract pictures, we call it pirate games. And all they have to do is tell us what side of the screen the pirate appeared. So it appears, it disappears, and then we vary them to what side, and they tell us without that first. Unbeknownst to them, there are three different pirates, each of which, when they didn't trial right, and they're almost at 100% accuracy, they're associated with different amounts of monetary gain. A single coin, a handful of coins, or a whole bunch of coins. We used to have dollars, but the adolescents started doing arithmetic to see how much they had gained after every single trial, so we made it abstract in terms of these coins. And so over the course of the experiment, again, these participants don't know about this pairing between stimulus and the amount of money they earn if they get the trial right. What you see is over time, That's from here, beginning of the task. By the end of the task, we see that they indicate what side of the screen is. The pirate was on with just a single coin. You're slower and slower to even respond to that, to answer that question. But we see faster reaction times when we say what side of the screen was the pirate, which, again, we didn't tell them, but was associated with Barnard. We debriefed them after and asked questions, and only a handful could tell us that there was some kind of matching between the pirate and the amount of points, but none of them could tell us the exact pairing. So this is how rewards can actually, IQ association rewards can drive our behavior without us even being aware of it. So now let's just look and see how have we seen in large rewards this represented in the brain. So this is looking at large relative to small rewards. And what we see is that adolescents are showing an exaggerated signal in the nucleus accumbens, an area that was shown in those animal studies that we built our paradigm from, and also an area that's been implicated in processing of reward, risk, and rate. It is also the case, we talk about reproducibility in science. This is probably one of the most replicated findings that we see in the literature. Now, adolescents, this exaggerated response that we see to reward. I'll just highlight one because there were 250 participants who were scanned not once, but 3 times. So we have data within participants as well as between them. And we've been able to map out this peak in the nucleus accumbens activity, and that peak during the late teens maps onto the developmental trajectory of sensation seeking that I showed before. And this is important because the magnitude of activity in this area in adults has been associated with about to make a risky decision. And in that early study that I showed you, it was associated with self-endorsement of engaging in risky behaviors that we could ask in children and adolescents and adults, the likelihood of leaving a party with a stranger, and the likelihood of engaging in high-risk sports like rock climbing, or based on our conversation at dinner last night with Owen Jones, it could be, diving, swimming with sharks, skydiving, yeah, and the list goes on. I wonder how you would have performed on this task early on. Okay, so the question is, I just showed you the sensitivity to reward, but the question is, how do cues that are associated with positive outcomes, how do they impact our actions? And so one type of social cue that we associate with positive outcomes, and particularly for adolescents who are so susceptible to and so focused on their peers, are social cues such as a smiling face. So we took the go, no-go test, the whack-them-all test that you did, and we used social cues. And so about half the trials, you had to refrain from responding to a rare neutral face, and half of them you had to refrain from responding to a rare smiling face. And we looked at overall performance to start with, and what you see is that children are more impulsive overall than adolescents who are more impulsive than adults. And if we look at the neural correlates using brain imaging and functional MRI, what we see is the neural correlate of this is in an area in the prefrontal cortex that's been implicated in impulse control. And so when children are accurately performing the task, they're activating this region more than adolescents or adults. So this is just for correct trials. Now, we looked at our data, and particularly we're interested in these positive social cues. And we saw a very different pattern when we compared the number of errors that you make to a smiling face versus a neutral face across these different age groups. We saw that adolescents are far more impulsive to these positive social cues relative to the neutral. This is a pattern that we didn't see in the children or adults. And when you look at the neural correlates, the suspect is, and it ends up being, the exact same area activated more in adolescents that was activated to reward is activated when they get these positive social cues. So basically what I've shown is exaggerated behavioral and brain responses to positive social cues during adolescence that are occurring when the prefrontal cortex is still showing these functionally significant changes with age. Now, I just showed you social cues, but Larry Steinberg has a whole body of evidence with regard to bringing a peer in and having to perform a task. And he came up with a game that we've all played, and that is, do you or don't you go through the yellow light, right? And so the beauty of this experiment, however, is that Steinberg had individuals perform it alone or with peers. And then he examined how many risky decisions when they were going through the intersection when there was a yellow light, and how many crashes the individual actually had. And so I'm just going to plot for you those data. But what I want you to keep in mind when I plot the risky decisions on the left and the crashes on the right is alone is in blue bars, and when they're with peers in red. And if you focus on those blue bars, adolescents are just fine on this task, no different from the other ages when they're alone. But when they're with a peer, that's when you see their performance is diminished. So this is one of those examples of cognitive performance is fine alone, and this emotionally, socially charged situation diminished. And if you look in the brain to look at the neural correlate, once again, this area in the nucleus accumbens pops up. So we see an exaggerated response in this region when adolescents are making a risky decision when they're with a peer. And I want to contrast this with a pattern of activity that we saw in the older adults, those 24 to 29. And here what you see, overall on the task, whether they're alone or whether or not they're with a peer, they're performing this like a cognitive task, and they're actually recruiting regions of the prefrontal cortex that we know are involved in impulse control and decision making. Now, I've focused on reward and games, but when young people come into contact with the law, often it's under conditions of threat or stress. And so I want to focus on stress first, and then I'll talk about conditions of threat. And we know from a large body of research, stress is any change that causes physical, emotional, or psychological strain. And we know from this literature that there's really the sweet spot. A little bit of stress is good, not any tension, it can be boring. But if you have high levels of stress, we know, particularly from the animal literature, that neurochemicals in the brain change. And the prefrontal cortex is an area that is really susceptible to high levels of stress, and it can basically take the prefrontal cortex offline. And we also know from animal and human research that adolescents are particularly susceptible to stress. So I want to illustrate for you the effects of high versus low stress on performance on an impulse control task. Again, I'm just building on that original whack-a-mole task. So this is even a simpler, easier impulse control task. You're responding to any letter of the alphabet that appears on the screen, but you refrain when you see the letter X. And so it's a rare non-target that you have to inhibit from responding. And the way that they determined when an individual was having a high stress day versus a low is they used smartphones. And so throughout the day, starting early, on a Likert scale from 1 to 7, they rated how stressful their day was or how low the stress was for them that day. And then they would bring in individuals on high stress days and also bring in individuals on low stress days. And what we see in the behavioral performance is that on high stress days, adolescents were much more impulsive than the adults were on high stress days. And when we looked at the neural correlates for this, consistent with some of the animal research suggesting that high stress can lead to changes in neurochemicals that can impact prefrontal functioning, and we see a significant decrease in activity relevant with regard to the adult performance. Now, so far I've been talking about different brain regions where patterns of activity are correlated with specific behaviors. Sort of in real time, we're collecting both types of data. But I want to turn to talking about connections in the brain, or what we refer to as the functional connectome, and look at how it varies under different emotional states. And this is one of those studies. It's a little bit worrisome because we're talking about maturity. Even though I don't think the brain's stable, it continues to change. But we basically wanted to see if we could predict an individual's true age just based on the pattern of connectivity across the entire brain. So we used AI, or machine learning, to try to use any information that we had from the functional connectome to predict an individual's brain. And we did it in a neutral state, no emotion. And we can do a pretty good job being able to determine the true age of an individual just based on functional connectivity throughout the brain. But this model is only good if we can predict age in another whole sample, right? Completely different from the one that we trained our model on. And so the question was, how well can we predict true age when the individual is in a neutral state or when they're in a positive or negative state? The negative state was an awful thing that we did to them. When they were performing a go, no-go task, we told them we didn't know when, and we had no control over it, but there was this loud aversive sound. And I'm not going to play it for you because it's really aversive. It's somewhere between static when you're trying to hear, March Madness scores or things like that, and an alarm clock that you really don't want to hear early in the morning. And so you get a galvanic skin response of arousal, and they rated as negative. The positive state was, we said, we don't know if or how much, but you could win up to $100. You get an arousal response for that one too, and they rate that as positive. So now let's see if our model on one sample can actually predict the true age of a completely new sample. And what we see is we do an okay job of predicting the true age of an individual based on their functional connectome. But we do a lot better in the neutral state than we do in these emotional arousing states. And for me, the big question was, where is the model failing? Because where it's failing is saying someone's either older or someone's younger than they are. And so when we look at the model to see where it's actually failing to predict the true age, it's for adolescents. So we see a bigger effect where adolescents are predicted to be younger than they are when they're in an emotional state than relative to when they're in a neutral state. Now, there are many astute eyes in this audience, and you're looking at these data and you're going, hey, there are a number of people that look like they're being predicted to be younger. So then the question is, how does this less mature looking functional connectome, how does it relate to risky behavior or risk preferences? And so what I'm going to plot for you are risk preferences, endorsement of engaging in risky behavior, as a function of those who are predicted to be older, so those will be filled bars, relative to those who are predicted to be younger, unfilled bars. And what you can see is a main effect. Those individuals throughout these ages who are predicted to have a more immature functional connectome and emotional states actually had higher risk preferences. And this was particularly true for this gray zone, 18 to 21-year-olds, which in law, age of majority is 18. We can sign legal documents without having to get somebody to co-sign. We can vote. However, we can't purchase alcohol legally until we're 21, right? So it's really suggesting some change that's going on there. And this study was actually funded by Owen's MacArthur Foundation Research Network on Law and Neuroscience. But we wanted to dig a little bit deeper and look at behavior and brain in real time. And also our question was, are we overestimating the cognitive capacity of adolescents with this age of majority model that suggests that you have full cognitive capacity by 18? And is it the case that we see under emotional circumstances, our cognitive abilities actually show later development? And while we had rewarding and threatening situations, in the interest of time, I'll just present the threat data. So we had these cues of potential threat. And this was the cue that was rare that they had to inhibit a response to. We also had sustained conditions, that awful condition I told you about where they don't know if or when, but that loud, awful noise is going to occur while they're trying to perform this impulse control task. And what we see in performance for these two conditions is that 18 to 21-year-olds, like younger teens, show diminished cognitive performance on this task when there are these conditions of threat. And if we look at the neural correlates of this to try to see what's going on in the brain, what we see is just like with the driving task that I described, what older adults were doing, those older adults are actually recruiting lateral prefrontal regions of the brain that have been associated with decision-making and impulse control. And what the younger ages are doing is they're recruiting cortical regions that are part of the limbic circuit that involves emotional processing. So it's more like an emotional task for the younger ages. It's more like a cognitive task for the adults. So the data that I just showed you, showing sort of peak changes during mid to late adolescence and extending into the 20s, sort of maps onto the age crime curve, where we see the most crimes occurring between the mid-teen years to the early 20s that I've illustrated for you here. And this is a reminder for me to be transparent and to tell you that the data that I presented so far is based on relatively healthy individuals. So what's the case with regard to those who engage in extreme behavior or who have antisocial or psychopathy related traits? Psychopathy is really rare in adults, less than 1 to 4% estimates of the prevalence based on the APA. But if we look at psychopathic traits and antisocial traits in young people who are involved in our justice system, what we see is that the majority of them show a decrease in those traits roughly from the ages of 16 to 24. In fact, there's other evidence that is showing that the majority of youth who commit crimes desist as they move into adulthood. And most importantly, because there have been discussions in terms of the Supreme Court about incorrigibility of young people who commit crimes, when individuals who have committed crimes have these traits, get youth-targeted interventions, they're focused more on more just and also rewards for certain goal-directed behaviors. We actually see, regardless of whether or not you're high or low on antisocial traits, you see a similar decrease in the number of violent offenses. So this is work by Caldwell that was published. So what these data actually suggest is that offenders may not be incorrigible, they may not be treatment resistant, or even less responsive to treatment. But it's about determining the right treatment and helping them get that. So now I just want to turn to how should we treat youthful offenders. And actually, there have been a number of Supreme Court opinions that have led to less harsh sentencing of young offenders. I already mentioned Roper. So Roper in 2005, and it was the years before that that really got me moving in that left turn in terms of my research. In 2005, we banned the death penalty for those under 18. In 2012, in Miller, we banned mandatory life without parole sentences for any crime. I'm saying mandatory because, as many of you know, you can still get a life sentence. A juvenile can still get a life sentence. It's not just mandatorily assigned to a particular crime or circumstance. And it's important for me to note that with these less harsh sentences, we have not seen an increase in violent crime, like some of my friends and family members have told me is occurring. In fact, what we're seeing, and I'm showing that in red arrows, in 2005 was Roper, and 2012 was Miller. We're seeing actually a decrease in particularly violent crimes. But again, it's still the case that states can decide whether or not to give life without parole sentences. And so you're seeing that there are 27 states that still permit giving juvenile offenders life without parole, so they have absolutely no opportunity to show that they've changed in any way. I'm not trying to suggest to you that some people may not show any change or should be paroled. And there's a case that's actually in the press now too, but the Crumbly case was sentenced to life without parole, and he committed his crime at 15. And his parents have also now been charged for that awful attack. Another area in which we see variability in state according to crime or the situation is the age of juvenile jurisdiction. And I grew up in North Carolina, but I've lived in New York for a while, and my two home states, only in the past few years, increased the age for juvenile jurisdiction of young people from 15 and under to 17. So that's North Carolina and New York. And also only recently have we seen changes in Missouri and Michigan, where they've increased the age from 16 to 17 being the limit. And then we still have 3 states where 16 and younger is the highest age of juvenile jurisdiction. And then we have Vermont, which is going in the other direction. And so for nonviolent crimes, they've actually been increasing the age of juvenile jurisdiction. They increased to 19 in 2022, and I think their juvenile justice system has to sort of catch up with the numbers, and so it's a graded change in terms of increasing to 20, but that's expected to occur. However, there is no, and this just blows my mind still, there's no lower age limit in terms of adult prosecution of a child. A toddler, a child of any age, could be transferred to adult court where they would get harsher treatment and sentencing. And I'm just showing you the different states here so that you can see those that are in light green have no minimum age for transfer of juveniles to adult court. And these are based on data that I could pull from 2023. If anybody has more recent ones, I'd love to know the direction that these statistics are moving in. It's also the case, I've been talking about juveniles, but it's also the case that I showed you data where 18 to the early 20s, we're still seeing neurocognitive changes and functionally significant changes in the brain. And based on this evidence, there have been a number of changes in the treatment of this, what I'll refer to as late adolescent class. Some people refer to them as young adults. And here's just a figure for you so you can see those states in green have some sort of criminal justice program for youthful offenders, 18 to 25. Those in orange have this combination of these types of programs and also a young adult court. The goal of all these programs is basically to align opportunities for accountability, which is important, but also remediation, given the special needs of this particular window of development for these individuals. And then also, we've had the opportunity to collaborate with an experimental young adult unit. So this is called the TRUE unit, for truthfulness, respectfulness, understanding, and elevating. And what they have developed is a program where 18 to 25-year-olds have mentors, and they're being prepared for successful reentry once released. And there is a stark contrast in the environment and what these individuals do. And you can see that here, traditional units, and also more socialization and interaction. And what's been really powerful to see is not only are we seeing improvements in these units for inmates, but we also are seeing it for correctional officers, and we're seeing more positive interaction between correctional officers and inmates. So even in the state of Connecticut, where 18 to 25-year-olds aren't juveniles, they are being treated in a special way because they have similarities with regard to some of their neurocognitive abilities, as do juveniles. And then there are also recent efforts to extend Miller, so mandatory life without parole. Can we extend that to those under 19, those under 20, those under 21, based on the evidence that's accumulating? And last year, I, with a group of really a number of distinguished individuals, held counsel with amicus brief, reviewing the developmental evidence, and we saw Michigan raising 1 year. So now, mandatory life without parole is for anybody under 19. And then this year, there was a landmark study Terry and I were talking about, and same groups of individuals with similar evidence. And my former graduate student, and now she's a professor and dean at UCLA, gave the oral testimony for this case. But in Massachusetts, we saw them raise the age for mandatory life without parole to under 21 from under 18. So the last thing I just want to note before I summarize is that if you've not seen this paper, I encourage it for law students and courses. This is a paper that came out, I think, just last month by Beth Kaufman, and it's looking at justice-involved youth and how we treat them and the recidivism rates, whether or not we're looking at rearrest or we're looking at their incarceration. And so I'm just going to talk about one of the studies that they highlighted. It's a study referred to as the Crossroads study. So they look at individuals who have committed similar crimes, and they look at the outcomes of those individuals. It's their first arrest. They look at those individuals who were processed formally compared to those individuals who committed similar crimes and they were actually diverted from the system and given intervention and remediation. And what you can see, and many times these youth get rearrested for just very minor, I'll call them crimes or violations, but you're seeing almost a 40 to 50% decrease in incarceration for those individuals in blue. They're the ones who were diverted from the system. So just to summarize, the science shows we see changes throughout the life course. I can't underscore that enough, but particularly during this period that extends throughout adolescence. There's also empirical evidence to show that there's diminished cognitive abilities in these emotionally and socially charged situations. And that shows continued development into the 20s. That's paralleling changes we see in the brain, convergent evidence. But you do see adult-like performance in adolescents when they're not in these emotionally charged situations. And then importantly, with regard to law, is we do see that decline in extreme behaviors and decrease in antisocial behavior. But with targeted interventions, we see an even more dramatic decline. So I think that hopefully these findings highlight the importance of a neurodevelopmental approach in the treatment of justice-involved young people to improve not only their outcomes, but also societies. So I want to just end by thanking the many institutions that have supported me throughout my career in much of this research, particularly the MacArthur Foundation and network that Owen Jones led. And I also just want to give a very special thanks to the Weaver family. And thank all of you.